Happy Wednesday, BC Calculus. Mr. Allender here with today's notes, and and so we'll start off with a quick recap of where we ended last time. If you remember last time, we're in section 9.8. I think I accidentally took that off, and it's power series as a function, looking at a power series as also a function at the same time, and we're going to develop this over the next couple of sections. So if you remember, what we did was we talked about how you could represent a power series. You could think of a power series as a function of x, but it only gives you answers in certain circumstances, like this one we had before. If you plug in 0.5, you actually can get an answer, but if you plug in 2, it just gets infinitely big. And so you have this thing called the domain of a power series, which is all the values of x that make the series converge. And we found out that there's different possibilities. It could be just one point that works. It could be all values of x that work, or it could be an interval with open or closed and boundaries, and that interval will be centered on whatever the center of the power series expansion is. So and so, like in this case, it's going a unit of 1. I'll mention again, but what we'd say is 1 is the radius of convergence. I don't think I used that vocab word last time, so I don't know why I'm getting that control shift thing there. That's weird. I don't know. Okay, moving on. But so that'll be distracting, but I'm going to move on with my life because it'll still work. So 1 is the radius because it goes 1 out from 0. Now let me just try one thing and see. Does that help at all? Nope. Okay, moving on. All right. And then we did a problem, and the key to finding the interval of convergence is first doing the ratio test, and then checking the endpoints to see if they work, and that's the problem we did last time. All right, here's a sample problem. If you feel like you remember how to do this, you could just take it on, or I'll start doing it, and I think because of all the writing, I'm going to pause it, and I'm going to work it out, and then show you the answer. Okay, so first I just wrote out what this series would look like. So I just wrote out the first few terms, kind of an interesting little series, just plugging in n equals 0, n equals 1, n equals 2 in, and because of the 2n plus 1, you get every other term instead. It's kind of, I don't know, a little interesting. And then, but we're still finding the interval of convergence the exact same way. We just do the ratio test. So remember, like, you're going to do a n plus 1 in the numerator. So you're going to put an n plus 1, right in there for the n. And so it'll be x to the 2 times n plus 1 plus 1. So I'm doing what would the n plus 1th term is, and that means turning all these little n's into n plus 1s. And so you can see how that's going to end up being x to the 2n plus 3. So I didn't bother showing it again, but you do the same thing down here. This little n becomes an n plus 1, and so you'd end up with 2n plus 3 factorial once you simplified. And then just an on the bottom, a little flippy trick action, and then there'd be a lot of canceling. And keep in mind, that's why we went over factorial canceling at the beginning of this chapter, is that you'd cancel this out, and this would be, like the bottom would be 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n, and so on and so on. And so everything would cancel out except for the, made a little mistake here. I spotted it. That's over 2. That should be, let me blow that up. That should be, there we go, x to the 2n plus 3 times 2n plus 2. In the bottom, everything else would be canceled out here. So now we're going to plug in values for x into this series to try to make it work. And then, but we're making sure that values of x are going to make this thing converge, which by the ratio test tells us that this has to be less than 1 as n goes to infinity. And if you think about it, no matter what x is, you make x equal to 1,000, that if you make n go into infinity here, it's still going to overcome anything that we put in for x. Any regular number we put in for x, we're going to go past it and put in something much, 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 much bigger. And so this is always going to be less than 1, because this limit is, in fact, I should just say, the limit is 0, which is less than 1. So no matter what I put in for x, then the ratio test is going to say it converges. And so this is an example where the interval of convergence is negative infinity to infinity, because I can put any values of x in and this thing will converge. And so I don't even need to, I don't need to bother checking the endpoints. I can just do this and be done with it. If you take a look up a bit, you'd say, oh yeah, because the factorial was in the bottom. And so this thing was really likely to converge because with a factorial in the bottom, it's going to be very easy for this thing to cancel. So that was kind of the sign that this thing was converging, and it was converging all the time, no matter what x is. Okay, moving on. Now we're going to talk about differentiation and integration. It's pretty easy. It's mostly going to be doing similar stuff. So, once you've made, remember, we're making power series a function. We're thinking of like in this example, we're thinking of the function of x being this power series to find out what the value of x is. And so since it's a function, we can integrate it, we can integrate it, we can differentiate it just like any other function. And so we can start playing around with these things. Just a couple of notes. One thing is the radius of convergence doesn't change when you do so. So that's kind of cool. You're not going to have to do the ratio test for every single function. Like you have to do the ratio test once, and once you've done it once, then any derivative or integral will have the same interval of convergence, radius of convergence. But the interval could change because the endpoints can work or not work, and they can go back and forth, and we don't have a set rhyme or reason about what's going to happen with the endpoints, and so you'll have to check the endpoints for each one. And a cool thing is you can integrate or differentiate the original formula, or you can work term by term, whichever you prefer. I'll show you that. And when integrating, treat x minus c as a variable. You'll see this as an example too. So here's a problem. There's my little function, and it says find the intervals of convergence for all of these things. So why don't you do the ratio test on this one and find the original's interval of convergence. And so you've got your formula there for an, and so you can do the ratio test. And I'll pause it and let you do that. Presto, there's the interval of convergence. Wait, where's all my work? Well, I'll be honest, I realized as I started the problem, I was like, wait a minute, I've done this before. We did this last class. So if you forgot, then hey, then you got a chance to practice this. I don't have too much of a problem with that. But we worked this out a couple days ago. We got the interval, the radius of convergence being 1, and then we found out 1 worked and 1 diverged, -1 converged, and so therefore we have the interval of convergence. Awesome. So now we're going to find the interval of convergence for all these other functions. So I'm going to do f prime first. And so f prime of x is, and I'm just going to do it term by term here. So I'm going to go through and just do the derivative of this thing. So I'm going to do, I want to show that as one example. So this is x to the 1, so that'd be 1 plus, and then multiply the 2 down, and that would be x plus, and then multiply the 3 down, and that would cancel, and so that'd make x squared plus ... Hey, wait a minute, I've seen this. This is a geometric series with the ratio of just being x. Well, I know when a geometric series converges because I know this series. And so I know it's from -1 to 1. Oh, you can see it's the same one. But the only difference is that now it doesn't work at -1 or 1. Remember that the ratio x has to be between -1 and 1 exclusive. And so the new interval of convergence is just -1 to 1. So that one I was able to figure out just taking the derivative term by term, and I could totally spot that the interval of convergence was -1 to 1. And I could do the same thing with f double prime of x and say, well, what's that? Well, that's going to be 0, that's gone, plus 1 plus 2x plus, and the next one will be x cubed, so that'd be 3x squared plus ... What's the interval of convergence of this? Now you might think, oh, I've got to do a ratio test, but that's the cool thing is I already have the interval of convergence worked out in terms of the radius of convergence. I just need to know the endpoints. If you plug in 1, you get 1 plus 2 plus 3, that diverges. If you plug in -1 for x, you get 1 minus 2 plus 3 minus 4, which is also going to diverge because the terms aren't getting smaller. And so now the interval of convergence is staying -1 to 1. Finally, we have to do the integral, and I just wanted to show it as a, as a little bit of variety. I could integrate these terms term by term and do it that way. But if I did that, what I end up with, I worked it out ahead of time. But I got to find the page that I worked it on. Here it is. If you integrate this term by term, the integral of f of x would be some constant, but that doesn't matter for convergence or divergence, plus, and then it would be x squared over 2 plus x cubed over 6 plus x the fourth over 12. That's if I did it term by term here. And so one question you might have is, well, yeah, does this thing converge or diverge when I plug in 1 or -1? Well, I can just look at it by inspection plus ... and I can say, scroll, for x equals -1, with it being some constant, which I don't really care about, and it would be the integral of f of x is 1/2 minus 1/6 plus 1/12 and plus ... And by the alternating series test, it converges. If they say explain why it converges, I'd say because the terms are getting closer and closer to 0, and the absolute value of the terms is always decreasing. So it converges there. But now x equals 1 is kind of trickier. So the integral of f of x is 1/2 plus 1/6 plus 1/12. It's kind of tricky to just kind of spot this off the cuff. My first thought about it would be that it probably converges because these things are getting small really fast, but I'm not really sure. So just to show how I could see it in a different way, I'm going to do it now, and I'm going to integrate this using not term by term. That's the way I've been doing it. I've just been using each term. I'm going to do it straight with the formula. So the question is, what's the integral of, where is it? There it is, of x to the n over n. And now I'm going to generate this series this way instead, just for some variety here. Well, that would be x to the n plus 1 over, and then I'd divide that down, so I'd have n plus 1 times n. Right? That would be the generic term there, and it's the sum of that, because we're doing the sum of this thing, from n equals 1 or 0? 1 to infinity. Okay? And so I'm looking at this sum now, and now I can say, all right, well, I only really care, though, when x equals 1. I'm not really worried about any other time, so I can just turn the x's into 1s, and so that would be the sum. And this is what this series is. It's just I couldn't recognize it because I couldn't see the pattern well enough, of from n equals 1 to infinity of 1 over n squared plus n. What do you think? Converge or diverge? And I hope you're getting a little bit of intuition here where you could say that converges. I could do a limit comparison. The easiest one, I mean, you could do a direct comparison. No, you couldn't do direct comparison very easily, but a limit comparison would be pretty easy. That limit comparison with 1 over n squared, this thing has to converge. Because limit comparison with 1 over n squared, if I ignore the n for a moment, pretend that that's not there, that's going to converge by a p-series. And so with the plus n, if you do limit comparison, you'll see that it converges. So that means x equals 1 also converges. Also converges. And so my interval of convergence of this thing was -1, because I found out up here that that worked, to 1. And now they both work. So that's the idea with this, is that I'm just going back to my little summary above. So let me scroll. There we go. So the radius of convergence doesn't change when you integrate or differentiate. The interval of convergence can change.